Welcome to the movie Creation of the Earth. This movie, we're going to explore how the Earth formed and how the Earth's waters formed, starting from the Big Bang through geological time. As you see behind me, I'm in Sealy's Bay, Ontario, right in front of our beautiful lakes that were formed by the last ice ages thousands of years ago. And you see all the algae in the back. Hope you enjoy the movie. Oceanography is the study of the oceans, the water, the lakes, and the hydrosphere. Now, there's four main types of oceanography: the biological components, the chemical, the physical, and the geological components. And we're going to see how all of these change over geologic time formation with the formation of the earth, water, and the way it goes today. So let's start with the Big Bang. Alrighty, so it all started approximately 13.7 billion years ago when all there was a tiny speck of matter. And this tiny speck of matter was actually very taut and dense. And it led to the creation of the universe. And this speck that we say that started this universe is known as the singularity. Now, once this explosion occurred, this ended up creating a large explosion, and after 1 second of this explosion, this led to the universe being a scorching 10 billion degrees Kelvin. And during this period of time, there was the only things in the universe were the elementary particles, such as protons and electrons, that were formed. And these particles were too energetic at the time, so they couldn't actually form the atoms at this point in time. However, after another 100 seconds later, the universe cooled to 1 billion degrees Kelvin, which for sure is definitely hot, but it's definitely dropping exponentially, so it's actually not going to be staying as those protons and electrons. Instead, afterwards, during this process, and when it was a minute after the Big Bang, there was a process known as nucleosynthesis, which occurred. And this nucleosynthesis, we say, is known as the period after the Big Bang, which elementary particles formed to create heavier elements. And this was during the time when the actual universe was down to a temperature of 1 billion degrees Kelvin, and this created these elementary particles actually created stable isotopes such as deuterium. And the majority of the protons were still not combining with the hydrogen nuclei at this point in time. So if you see at the top left there, you see that a proton and a neutron will create a deuterium, which is an isotope of hydrogen. Now, as we move forward, we're moving up a little bit in time. However, the atoms begin to form, such as hydrogen and helium, as you see in the photo here on the screen there. And deuterium, hydrogen, helium, and even lithium begin to form. But after 379,000 years after that Big Bang, radiation, which is known commonly as cosmic background radiation, separating from matter today, which continues to create the universe, and even today as we move forward, as it accelerates in time. So you see the protons here. Now, over billions of years, stars began to form after this process and used hydrogen and helium to convert it into heavier elements that we see today, such as carbon, nitrogen, and oxygen. Now, this is when these heavier elements actually get used in oceanography, which we'll see later on in this movie. And these stars will quickly die and actually explode into massive explosions known as supernovae. And these supernovae will create dust that will create new solar systems that we'll see later on at the formation of our solar system. And as you see, it all starts with those elementary particles moving to atoms, to stars, and will later form galaxies. Now, as you see here, these are nebulae. And these nebulae form after those massive supernova explosions, which is very important for us to understand about in this universe here. And as you see, here's the star beginning to explode, and then it'll create an supernova, which is an extremely big explosion, and lead to these new solar system formations. So now as we move forward a little bit in time, galaxies begin to form, and galaxies, which are created by clumps of stars and star systems, continue to form. And obviously, if these giant stars collapse over the star, when stars form, such as a red hot supergiant, this can potentially create a black hole. And these black holes are actually thought to be crucial for galaxy formation, and we'll see that in a little bit here as we see as our Milky Way forms. And there are 5 major type of galaxies, and they would be spiral, irregular, peculiar, lenticular, and elliptical galaxies. And the Milky Way galaxy is actually a spiral galaxy, just like the one on the image here. And you have the Milky Way shooting X-ray and gamma ray emissions. And then you've got some supernova, you have a black hole, that is actually sucking up a star when it's falling towards it. And we've got a nice spiral galaxy, and you've got a nice cluster of galaxies, including elliptical, lenticular, pellicular, and so forth. Now, our Milky Way galaxy contains approximately 200 billion stars. Now, a spiral galaxy and it's a spiral galaxy, and it has a flat disk containing 200 billion stars. Now, the thickness is approximately 1,000 light years with a diameter of an outstanding 100,000 light years. Now, remember, 1 light year is actually the amount of time light actually travels in a year, and light actually travels at approximately 3.0 times 10 to the 8 meters per second. Now, usually when we look at galaxies in the universe, they're usually found in clusters, which are groups of galaxies, and range from diameters of approximately 1 to 30 million light years. And superclusters can go up to 500 million light years in diameter. As you see these beautiful clusters of galaxies out in the universe. Now, as stars continue to form and die in that life cycle, we end up seeing what the universe is like in modern day, and we know that because of Edwin Hubble, who was a famous astronomer after his paper in 1929, and explained that objects were shifting away from Earth, which states that the universe continues to expand further and further apart. And this proved Einstein's theory of relativity, of how the universe cannot actually be stuck in one state, even though he wasn't believing this at the time. It proves that it was accelerating. And the motion of redshifting is when the wavelength of light is being stretched and it gets further away. So if you see something, or an astronomer sees something in the night sky that's going red, it's meaning that it's moving away from us. And if it's going in a blue shift, it means it's actually coming towards us. And the universe is actually continuing to expand and contains 30% dark matter, 65% of some dark energy, which we're still trying to figure out today what this would be, and 5% of the energy, in which matter is the composition of stars and planets that we see. And Edwin Hubble was the one who actually first published the paper, while this proved Einstein's theory of relativity in terms of the universe not staying in one state. Now, as we move forward, now we're going to try to go narrow down towards how did our Milky Way galaxy form. Well, we know that it's a spiral galaxy, and it actually formed approximately 13 billion years ago, and began by some protogalactic cloud that was roughly spherical in shape and formed stars. And we'll look more towards the formation of the stars as we look at our own solar system. But as this protogalactic cloud collapsed, it led to some disk forming, and actually was collapsing due to the conservation of angular momentum and how it was shaping towards kind of a spherical shape. Now, the stars in the center of our galaxies are also known as a halo from the globular clusters, and were first formed approximately 12 to 13 billion years ago. Now, forces that were actually gravitational forces caused gases to form into clouds and clumps, similar to what star clusters are like. And the clouds formed stars and other solar systems in our galaxy, which we'll see in a moment, into the formation of the solar system. But the collapse said to last a few 100 million years, and the younger stars and older stars in the center of the galaxies are actually similar in age, which is kind of weird in a way, but at the same time, obviously they're going to be older and more similar in age than our sun, as the sun's more towards the outer bands of the galaxy. And stars continue to form today, and the spirals and the arms of galaxies, and these were the shapes that it took for angular momentum to flatten out the disk of the galaxy. Now, the formation of the spirals is interesting because obviously we knew that stars after time continuously die, release gas, and form new solar systems and stars. But it was due to the fact that the differential galactic rotation, which really states that the stars, when the stars are actually moving towards, where they're located towards the center of the galaxy, they're actually orbiting faster than the ones on the outer edge of the galaxy, and at this time there was less turbulence, which led to more rotations with the stars and gas, forming the disk, eventually leading to the spiral formation. And the spirals actually formed approximately 3.6 billion years ago. And as mentioned before, black holes are actually thought, especially supermassive black holes, to actually help with the formation of galaxies. As we see in the middle, there is a black hole, and it's actually known as Sagittarius A. And the solar system, as we saw, it was located in the spiral of the arms of the Milky Way galaxy. Okay, so now we know how the galaxy formed, but how did the solar system get here? So we can try to see how the Earth formed. Well, this all started from a nebula produced by supernovae approximately 5 billion years ago. It became obviously spherical due to different processes, but it began to rotate and started to collapse under its own gravity. And we're actually going to see how it forms in just one sec here. So, approximately 4.6 billion years ago, the solar nebula began to collapse due to its gravity. Now, the composition at this time was only mainly hydrogen and helium, and because the majority of the material fell towards the center of the nebula, it was getting extremely hot, dense, and concentrated at the time, and the hot temperatures led to vaporization of the solid material in our solar system. Now, after this nebula contracted, the nebula begins to shrink and rotate faster and faster and produces some disk. And this is because there was an increase in velocity and is known as the nebular disk section. Now, the process, like mentioned with the formation of the galaxies, is known as the conservation of angular momentum. And this states that the measure of motion of a rotating object in terms of its speed and how widely the object's mass is distributed along its axis, which it's clearly doing in this case because of the fact that it's rotating faster and faster within its own axis. And obviously, as the turbulent motions and magnetic fields through the nebular disk decreased the angular momentum, this obviously lowered the speed of the materials in the system at the time. Now once the gravitational energy comes to a halt, which was fueled by the heating of the stellar nebula, the nebula began to cool. Now, obviously, the center of the nebula, where the concentrations were absolutely dense and heated, this was leading to the creation of our magnificent star, the sun, which maintained high temperature and its own energy, as we see in our modern solar system, and the process took approximately 50 million years. So we're not done yet, because how did the planets and asteroids get into the solar system? Well, the disk was still left in a protoplanetary disk stage, which originated from the formation of the sun. Now, these leftover dust and gas particles then started to bombard with each other, eventually creating larger objects leading to planetesimals, which you see. And a planetesimal is some object that can range in different sizes that's usually at least a kilometer to hundreds of kilometers in diameter, wide, that continued to bombard one another, and this was obviously formed by leftover dust and gas particles at the time. Now, once these actual planetesimals grew approximately a kilometer in diameter, they began to create a force, and that force is gravity. Now, obviously, the larger the planetesimals, the larger the gravitational force would occur at that time, which means that there would be pulling more gas and dust particles, eventually creating mighty giant planets. And this process lasted for millions of years. But now that we see that our sun formed and how our planets came to be, what about the asteroids? We've got the asteroid belt between Mars and Jupiter and the Kuiper belt. Well, obviously the asteroid belt was formed by the remaining dust particles and rock that weren't formed in planetesimals. Now, the asteroid belt that we see orbiting between Mars and Jupiter are actually being kept by Jupiter's resonance. And Jupiter's resonance actually keeps all of these asteroids intact, orbiting around the sun. And the asteroids are mainly contained of metals such as nickel and iron, and are also thought to contain water, which is why it will be very important to the creation of our earth and water as we see that we move forward. Now, the chemical composition was basically looking from the inner planets, which are Mercury, Venus, Earth, and Mars, really had rock and actually metals such as olivine and the metal oxides. But between that ice ring, which is formed between Mars and Jupiter, if anything's formed past Jupiter, they would be forming ice compounds that were carbonaceous, so they were not hot enough to actually create rock. And on the asteroids, sulfur, hydrogen, and carbon-based silicates formed within the solar system. And water actually began in our solar system when the cold temperatures let oxygen molecules to form with hydrogen. And if they were obviously far enough beyond Saturn, for example, they would be creating ice. And other ices also formed, such as methane and ammonia, because carbon and nitrogen were able to bond with hydrogen. So now that we know how the solar system formed, let's start about talking about the Earth's formation. So it formed 4.6 billion years ago, and this marked the beginning of the Precambrian era. And at this time, as you see, there was only a whole big molten ocean of magma. So it was certainly not a time that life could sustain itself on the Earth. And at this point, there was still no solid core of the core crust on the Earth until planetary differentiation occurred, which separated the different layers of the composition, both chemically and physically. So now we're going to go into the Precambrian era from approximately 4600 to approximately 540 million years ago. So the formation of the Earth's core and crust was due to planetary differentiation. And what happened was that the heavier metals such as iron sank towards the core of the Earth and let the lighter metals such as the silicates rising up and cooled, forming the Earth's crust. Now, there are three major parts that are broken into 5 layers of the Earth. You've got you've got the inner and outer core, which are iron based. You've got the mantle, which is broken up into the mesosphere and asthenosphere, which are mostly solid and plastic like silicates. And then you've got the lithosphere, which is the Earth's crust. Now, speaking of the Earth's crust, the Earth's lithosphere is actually interesting because there's two types of Earth's crust, which would be the continental, that is thicker crust. However, it's less dense with an average density of approximately 2.7 kilograms per cubic centimeter, while the oceanic plate is actually more dense with an average density of 3 kilograms per cubic centimeter. However, as you see, it's a lot thinner than that continental crust. So as we move forward to approximately 4.5 billion years ago, there was a big collision known as the Great Impact Hypothesis, which is highly accepted by many scientists to this day. They thought that during the formation of the solar system, another giant planetesimal known as Theia collided with the Earth, which led to a huge chunk of rock being released from the Earth and eventually got caught into the Earth's orbit. Now, it was this moon, obviously, as we see in the sky today, is very important to the Earth as it slows down the rotation rate and is caused by friction between the two objects, which actually result in tidal forces as we see today. And because the energy continues, it's actually pushing the moon a little bit away from us, teensy bits at a time. It's hard to tell, but it actually has been proven by scientists. And because once this formed, the moon formed, this made the Earth revolve extremely fast at the beginning, obviously, with one day equaling a couple hours long, and formed our magnificent moon that we see. So as we move forward in time, the oldest meteorites were found approximately 4.56 billion years ago, and the Earth at this time was constantly bombarded by asteroids and comets. Now, the oldest moon rocks are dated to be approximately 4.44 billion years old, and the oldest single mineral, known as zircon, was discovered to be approximately 4.2 billion years old. And some of the oldest rocks that you can find today can be found in modern-day Canada, Africa, and Greenland that were approximately formed 4.3 to 4 billion years ago. And zircon is something that was approximately formed 4.2 billion years ago. However, there's not actually much known on it as we continue today, although geologists continue to wonder and research on what zircon actually, where it's from. So now, as we talk about the Earth's formation, the Earth's atmosphere was formed 4.6 billion years ago, and it was mainly and because of the major volcanism at this time, the majority of the gases actually contained hydrogen sulfide, methane, and lots of carbon dioxide. And it's actually approximately 10 to 200 times of the amount that we see today. And obviously at this time, we didn't actually have water. However, it's kind of like thinking about what Venus is now with all of its sulfuric acid. So now as we move forward, now we have a question, and it's a very important question. How did the Earth's oceans form? Well, it occurred in the Hadean period during our Precambrian era, approximately 4.4 billion years ago. And as the crust formed, lots of volcanism has been going on through these times, leading to volcanoes erupting. It actually released a lot of water vapor, and it got released into the Earth's atmosphere, which led to the cooling of the Earth's crust and began to rain for centuries. And as the rain fell for centuries, it dominated a lot of the Earth's surface and actually stayed on the Earth due to Earth's gravitational pull. But as Earth continued to get bombarded by asteroids and comets, it's also said that water came from these objects as they collided from the Earth. And during the formation, some asteroids had oxygen combined to hydrogen, like we've seen before, to create water. And it goes the same for comets, although it's mainly ice, which actually would have melted into our atmosphere. So now that water exists on the planet Earth, life is able to spark up, as its existence is thought to be estimated to be on the planet from 3.8 to 3.5 billion years ago during the Archean period in the Precambrian era. Now, these organisms that were formed were bacteria-type organisms and mainly probably based by RNA, and were formed under these undersea alkaline vents, which are undersea vents where seawater met with the metals that were forming under the Earth's crust, creating a reaction with the warm environment, yielding hydrogen. Now, as the Earth's earliest life form obviously occurs, they were mainly prokaryotes, which are cells with no nucleus and can be broken up by bacteria and archaea. And the earliest bacteria found would be called as blue-green algae or cyanobacteria. And these cyanobacteria are actually larger than most bacteria, have a thicker cell wall, and once they're actually formed in larger layered structures, they're usually known as stromatolites, or rounded layered structures called onchylites. And they can actually secrete some calcium carbonate, which obviously would help with the seafloor and sediments. And later in geological time, cyanobacteria would help the amount of oxygen in the Earth's atmosphere. And this would be caused by cyanobacteria photosynthesizing, yielding oxygen, and occurred throughout the Precambrian era. Now, as life begins on Earth, so does the first continent, known as Valbera, and formed approximately 3.8 billion years ago. This continent is actually located mainly in South Africa and Australia modern day, in two separate cratons known as the Cape and Pilbara cratons. Now, before we move towards continents moving, we gotta look at continental drifts, and my good friend Alfred Wegener. Now, the Earth will change geologically over time due to lithospheric plates called tectonic plates, which are sections of the Earth's crust that move to the continents and create geological features. Now, Alfred Wegener proposed this continental drift theory in the early 1900s, and he was a German meteorologist who wrote a paper on this continental drift, with South America and Africa fitting like a jigsaw puzzle, finding that fossils actually appeared on opposite sides of continents, and other opposite sides of continents also had similar geological structures. And everyone at the time didn't believe him. However, it was actually led to being believed in the 1960s after J. Tito Wilson led with the plate tectonics theory with continental drift as an extension. So as we move forward in time, then another new continent, approximately 3.5 billion years ago, forms, called Ur. And it would contain mainly modern-day Australia, and it would be mainly composed of igneous rock due to the high amount of volcanism at this time. And because the crust kept growing and growing due to the volcanoes erupting, another continents actually began to form. And this other continent was known as Arctica, which actually is modern day Canada, Greenland, and Siberia. And you'll see how these continents move and change over geological time as we move forward. But another question that stumped scientists for a long time, and even to modern day, is how did plate tectonics even form? Well, the plate tectonic system actually is thought to start approximately 3 billion years ago. And these plates are actually thought to actually form similarly to subduction zones, which we'll look into in a little bit, because of the slam pulls, convection, and magnetic currents pressuring the plate boundaries and weaker points. It led to cracks into the Earth's crust and led to our plate tectonic system moving. And the subduction zone is the convergence of a continental and an oceanic plate. So the oceanic plate is subducting underneath the continental due to being more dense. So as we move forward in time, we move to approximately 2.5 to 2 billion years ago to an event that's important, known as the Great Oxygenation Event. And it's caused by the cyanobacteria at this time producing too much oxygen due to the process of photosynthesis, which is converting carbon dioxide, water, and light into oxygen and glucose. And at the time, obviously, there wasn't much free oxygen in the atmosphere, as we've seen. However, most of that oxygen was forming with iron in the minerals of the earth, but there was a problem. The problem was that there was too much of it, that iron couldn't actually form with it, and it started releasing itself towards into the atmosphere, which actually was toxic to the anaerobic bacteria and began to poison themselves at the time. And actually, with oxygen not actually being abundant in the atmosphere, it bonded to methane to create CO2, which led to obviously some problems at this time. And this actually, due to the oxygen combining with methane, this warmed our planet drastically. However, as oxygen combined with it as well, it removed a lot of the methane that was in the atmosphere, cooling the planet, leading to an ice age. And this killed many of the unicellular organisms, including cyanobacteria themselves, that died. So the results of this great oxygenation event was the accumulation of oxygen in the atmosphere. These anaerobic organisms dominated, but they were vanished to the bottom of the ocean where not a lot of oxygen existed at the time, and is also known as the prehistoric mass extinction. As we move forward in time to approximately 2.7 billion years ago, the first eukaryotic cells, which means that these are usually cells with a nucleus, began to form due to a theory called the endosymbiotic theory, which states that when larger cells engulfed or ate smaller cells, the smaller cells were not digested, and they actually lived inside the larger cells, which created a symbiotic relationship, which is explaining how two different organisms had a close biological interactions. As we move forward to approximately 1.5 billion years ago, the first fossil evidence that was found with the cell nucleus, which are the eukaryotes, led to more complex organisms being able to form on the Earth. And at this time, oxygen began to be more abundant, which also helped more complex organisms form. As we move forward to 2 billion years, two new continents formed named Baltica and Atlantica. Now, Baltica is thought to be found in parts of modern Western Europe, while Atlantica is thought to be found in southern and eastern South America and western parts of Africa. And this actually led to a new continent forming 1 billion years ago called Rodinia. Now, approximately 1.5 billion years ago, Baltica and Arctica collided to create the formation of Nina. And over that 500 million years, Atlantica and Nina collided, creating Rodinia, which also created a snowball Earth at this time due to the geographic location. So now that the continents are beginning to shape up and get larger, the earliest shelled organisms and first invertebrates formed 750 to 700 million years ago. And invertebrates refers to any species of organisms that actually does not have a backbone. And some of these organisms at the time include trilobites, which you see on the screen there, some fish species, and mollusks. Now, trilobites were animals that had soft body with a shell, and some of the fish species at the time were known as agnathans, which are members of the nekton, which are swimmers of the sea. Now, agnathans were fish that didn't have jaws and fins, but they had lots of bony scales and plates with a cartilaginous skeleton. Now, mollusks are marine animals that typically had shells, and some of the mollusks that existed at this time were scallops and clams. Now, as we fast forward to 650 million years ago, another supercontinent by the name of Pannotia formed, and was formed when Rodinia broke up into different continents, into two major continents, Proto-Gondwana and Proto-Laurasia. And at the time, major glacial periods occurred, existing by the poles, creating two proto-oceans by the name of Panthalassa, which is modern-day Pacific Ocean, and the Pan-African Oceans. and approximately 540 million years ago, Pannonia broke into 4 different continents known as Gondwana, Baltica, Siberia, and Laurentia. So now we're going to be moving towards the late Precambrian era, and on the seafloor, many shelled organisms and invertebrates such as mollusk species of fish like the agnathans, trilobites continued to grow in numbers. But parts of the seafloor had forests of fern-like plants, which gave some nutrients to some of the species of animals on the seafloor, such as carbon, leading to some organisms producing photosynthesis. And this continued into the Paleozoic area and led the trilobites to dominate this world. Now, with this being said, a big event called the Cambrian explosion occurred 542 to 488 million years ago, and is thought to be the largest evolutionary explosion in geological history, because the increasing temperatures warmed the climate, increasing oxygen in the oceans, and formation of newer marine habitats were the main causes to this, which led to the trilobites being dominant at this time. Some of the first predators in the seafloor actually hid into the sediments to hunt for prey, and during the Cambrian period, there were lots more organisms that would have shelled that used a defense mechanism to hide from other prey. And one of the big predators, as you see, is called the Tamasiocaris borealis. And these predators were so large and looked like shrimp, and they were known as filter feeders and had large feather-like structures on their head that were used to eat plankton at this time. Now, these creatures had a big spine and were divided by smaller spines. But another predator that was existing at the time, which is the Herdia victoria, had a nickname of the T-Rex of the sea because it reached approximately 50 centimeters. But at this time, there weren't many big species of animals. It was a lot like very small organisms that could be as big as a thumbnail. And the term, and these trilobites at this time hunted, these organisms hunted trilobites and other benthos, which are living organisms on the seafloor at the time. And another predator which you see is called the Autoia prolifica. And most of their prey included mollusks and other shelled organisms and other worms, including themselves. Now, another worm by the name of Hallucigenia sparsa had spikes that resembled porcupines and went all the way on their backs. And approximately 505 million years ago, corals began to exist, and the earliest corals were built by mollusks and marked the beginning of coral reefs. But the difference that is now that corals actually are the ones that built coral reefs, but at the time in Precambrian there weren't corals, so mollusks actually formed them at this time. Now, 470 million years ago, the first plants went on land known as lichens, which is kind of similar to moss. And they actually have a symbiotic relationship between two different organisms, which are fungi and algae. And the plants led to photosynthesis and took lots of CO2 from the atmosphere, which leading us to a mass extinction known as the Ordovician Silurian. So as the movement of continents during the Paleozoic 500 million years ago, the continents Laurentia and Baltica collided to form Laurussia, and is including parts of North America and Europe. Now, this later formed an Acadia Oregoni, which is the Acadia mountain range, and an Oregoni is where sections of the Earth's crust continued to form mountain ranges. And during this time, Gondwana moved northwards from the South Pole, as you see geographically here. Now, life during the Ordovician and Silurian periods were still lacking a backbone. Trilobites continued to live on the seafloor, and life continued to use shells as the defense mechanisms. However, clams used some dual shell system with shells on the left and right sides, but brachiopods actually evolved and had top and bottom shells while living in muddy areas. Predators during this time needed to have an outer skeleton that was rough, and an example of a predator at this time was known as the Euryptonid, and it was kind of like a sea scorpion that grew up to 6 feet in length and belonged to the arthropod family, and squids and it was also, and it hunted a whole bunch of different benthos and organisms at this time. Squids and octopuses that exist today evolved from the hard shelled organisms that existed in this period, and the first vertebrates actually formed during this period of the Ordovician. And the first organisms that were vertebrates are known as the ostracoderms, but they didn't have any jaws. However, they had protective plates that covered their bodies. As we move forward in the Silurian period, some of the algae continued to adapt on land, becoming the first world's plants that were terrestrial. Now, organisms continued to evolve while trilobites were still dominating at this time. The first vascular plants actually formed on the Earth approximately 430 million years ago. And these vascular plants are actually plants that have xylems and phloem, which helps with the process of photosynthesis. Now, on the seafloor, there were plants called crinoids, and they acted like trees. However, they're not actually plants, and they existed throughout the Paleozoic era, from the Cambrian to Permian periods. These organisms actually gave home to many species of organisms and fought for their food in big groups, and they caught their food by catching plankton through their arms that they had. So as we move towards the end of the Ordovician here, it's approximately 438 million years ago, a mass extinction occurred, known as the Ordovician Silurian mass extinction. This is thought to be caused by two large events, by glaciation and sea levels falling. And it's thought that the increasing amount of plants removed too much carbon dioxide, leading to the cooling of this Earth. The fall in sea levels are actually thought to create the Appalachians in modern day and resulted in a killing of 86% of the species of the Earth at that time, including trilobites, brachiopods, and graptolites. So, as we move forward after the mass extinction, modern day China splits apart from Gondwana and into two different continents from north and south. The movement Gondwana continues to move northwards, and it begins to shrink the Paleo-Tethys Ocean at this time. And as we move towards the Devonian period, the Euro-American continent collided with the eastern section of the Baltica continent, resulting in the formation of the Ural Ocean. And as you see, the movement of continents over time, North China keeps moving, and the shrinking of the Paleotethous Ocean occurs as well. So life in the Devonian period, so approximately 385 million years ago, fish finally became the dominant species on Earth. And at this time as well, the first insect fossils were also dated to be found at this time. Now, during this period, sharks began roaming the oceans approximately 370 million years ago, and the first plants that were associated with seeds were approximately dated 365 million years ago. And ocean continued to evolve with fish dominating through these times. Now, this eventually led to another mass extinction, approximately 364 million years ago. This mass extinction, known as the Late Devonian, was thought to be caused by the land plants releasing nutrients into the oceans, releasing large amounts of algal blooms. And these algal blooms lowered the amount of oxygen in seas and killed animal life. Now, this mass extinction resulted in 75% of the species that died, and this mass extinction almost terminated all trilobites and lasted hundreds of thousands of years. However, trilobites still could hang on. Now, at this time as well, the volcanic ash cooled the temperatures, killing the spider and scorpion species that lived on the land. After this extinction, it wasn't until 10 million years after that the vertebrae began to appear on the Earth's land masses. And the Alpistostegalians, which are the amphibians during this time, became extinct. So now we move forward into the Carboniferous and Permian periods. So after this mass extinction, the amphibians continued to increase, and the number of reptiles, such as frogs, multiplied in great quantities. And these reptiles began to live in swamps and coniferous trees and forests. 330 million years ago, coal swamps appeared, which are the forests in these times that later degraded to coal. Now, lots of aquatic reptiles, such as the mesosaur, who lived in the early Permian period, approximately 299 to 271 million years ago, were aquatic reptiles that were approximately a meter in length and had a long skull and tail. So as we continue to move forward now into the Permian period, the mesosaur ate organisms such as crustaceans. Now, sharks such as the Heliocoprion, which you see in the movie right here, existed 290 to 260 million years ago and were one of those main predators at the time that had sharp teeth that were in shapes of spirals, which we don't really see on modern-day sharks. Now, another predator that existed at this time was known as the placoderm, which were a species of fish covered in bony plates and lasted approximately 50 million years. So as we move forward, the formation of the commonly known supercontinent Pangaea exists and was formed due to the collision of approximately 300 million years ago when that Gondwana and Laurussia collided, forming Pangaea. Now, Pangaea looks like a sea, and this closed the Paleotethous Ocean, forming the Tethys Ocean, and formed the Appalachian, Ural, and Acadian mountain ranges that we're seeing more commonly today. Now, as these continents move, volcanism continues to exist, and approximately 252 to 245 million years ago, during the end of the Permian period, a big volcanic eruption due to Siberian traps existed, wiping 96% of the world's species of organisms at the time. Now, these volcanoes in the Siberian trap emitted too much CO2 and toxic gases into the Earth's atmosphere, resulting in drastic drops in the Earth's temperature. and the oceans became more acidic due to the lack of oxygen in the atmosphere at this time. And obviously when the ash was released into the atmosphere, it lowered the temperatures, and these burned coal deposits, also releasing CO2 into the atmosphere. Now this resulted in 96% of the species of animals dying, and there was only one species of sea urchins that survived, some ammonites and other organisms. However, this was the end of the trilobites as they became extinct. Now we're moving to the Mesozoic era as we move forward after this extinction 252 to 66 million years ago. And yes, this is the era where dinosaurs roamed the earth. But we're not there yet. After this mass extinction, approximately 250 million years ago, reptiles ruled the ocean, and an example was a large reptile known as the ichthyosaur, and they look like modern-day dolphins, but had long tails and swam side to side like modern-day eels, and are classified as nekton, which were swimmers of the sea. And approximately 240 million years ago, the first crocodiles actually began to roam the earth. So life continues in the Triassic period. 228 million years ago, the first dinosaurs got roaming onto the earth, and 7 million years later, mammals began to exist. However, the mammals at this time were only as big as mice, so it's not evolved to what we see today yet. However, we're getting forward, and approximately 210 million years ago, turtles began to roam and exist on the earth. Now, these reptiles became the dominant species of the oceans, while dinosaurs became the dominant species in the terrestrial world. Now, the majority of these reptiles that lived at this time were lizards that lived also on land, plesiosaurs, ichthyosaurs, and turtles. Now, as we move forward in time to approximately 214 to 299 million years ago, there were two events that scientists believe caused this Triassic-Jurassic mass extinction. And this is around the formation of the Mid-Atlantic Ridge, which was formed by the divergence of two tectonic plates, resulting in spewing lots of magma and basalt eruptions, causing another drastic climate change. And the second thing was a possible asteroid impact that existed during this time. It is said that this mass extinction resulted in approximately 50% of the marine species at this time. And as you see, this was due to seafloor spreading. It caused the Mid-Atlantic Ridge to form and change into the atmosphere. So as we move forward to approximately 200 million years ago, Pangea began to break up. And at this time, there was the Panthalassic Ocean and Tethys Ocean that were enclosed by Pangea. However, Pangea broke up into two continents, which is known as Laurasia to the north and Gondwanaland, and they were separated by a new ocean approximately 150 million years ago, known as the Atlantic Ocean because of the Mid-Atlantic Ridge. And at the time, India and Antarctica began to move away from South America and Africa. So life during the Jurassic period actually led to another surprise, that mammals that existed at the time surpassed the number of dinosaurs, and reptiles actually evolved into birds 155 million years ago. So the first birds actually existed around 155 million years ago, which is amazing to look at how reptiles evolved into birds that we see today. And a bird that evolved from a reptile, an example, would be the Archaeopteryx, which carried both characteristics of reptiles, such as their bony tail, claws, and teeth, and their birds with their wings, and the birds would have the wings and feathers. Now, during this period, also, the first flowering plants got into existence. Now, back to geological time here. Approximately 145 to 135 million years ago, the tectonic plates continues to move, with the South Atlantic Ocean beginning to form due to seafloor spreading. And remember that seafloor spreading is the divergence of two tectonic plates from mid-ocean ridges that rift and create new rock, leading to formation of new seafloor. Now, the Panthalassa Ocean, which I've said before is the Pacific Ocean to modern day, continues to decrease in size while the Atlantic increases, and India started to actually move northwards, beginning the closure of the Tethys Sea and formation of our modern day Indian Ocean. So, now a species that we see known as plankton that have existed for millions of years was actually evolving quite a bit during the Mesozoic era. So a species known as the coccolithophorids were microscopic and had skeletons composed of calcium carbonate. And the number of plankton actually increased drastically in the Cretaceous period, but when these coccolithophorids died, they would go to the seafloor, and with the pressure of the water and oceans, they create sediments such as limestone and chalk. And current day oil, approximately 60% of it actually initially came from plankton during this era. So life in the Cretaceous period, so approximately 145 to 66 million years ago, the very first marine turtles lived. And it wasn't until 120 million years ago that marine turtles are closely related to actually the sea turtles that we see in our oceans today. An example, which you see on the screen, is called the Archelon, which grew up to a length of 15 feet. Now, as we move forward a little bit in time, 115 million years ago, the flowers begin to emerge in large quantities, and 100 million years ago, coral reefs were getting really big, and still at the time were being formed by mollusks. And as you see, these coral reefs are still formed by mollusks, and some beautiful life evolving in the Mesozoic era. Now, the Mesozoic era had the phytoplankton on the base of the food web, which is showing where what eats what, pretty much. So, like, if I, for example, for humans, if they ate bird eats worm, obviously the humans would be at the top, and it would go to the birds, and then the worms at the bottom. So fish, reptiles, birds, and dinosaurs were larger predators at this time during the late Cretaceous, and a large predator known as the Xiphatinus was a large fish and was a carnivore, and had lived through the Cretaceous period and was carnivorous. Now, the prey actually had defense mechanisms such as spikes and beaks at this time, and evolved towards teeth and beaks at this as we move forward in time. So now we're moving closer to modern day at approximately 97 million years ago, where the North Atlantic Ocean continued to open and form along with the Caribbean. India continued to move towards Asia, however, hasn't collided yet. obviously decreasing the Tethys Sea. The Indian Ocean continued to form and grow in size, and the Madagascar actually got disconnected from India just before another mass extinction arises, known as the Late Cretaceous and Paleocene mass extinction. And this occurred approximately 66 million years ago, and yes, it's the one most of you would have heard of, created by a 6-mile wide asteroid that struck the Yakutan Peninsula. Now, the asteroid impact resulted in forming shock waves that unleashed megathrust earthquakes, which are earthquakes measuring greater than 7.1 on the Richter scale, mega tsunamis that reached unbelievable heights and ended up going extremely far inland. Now, the impact also created dust that went into the atmosphere from sulfur from vaporized rock and brought the temperature down, killing many species of animals. And these tsunamis were absolutely huge. But the sulfur that came from the vaporized rock resulted in acidic rain, which killed a lot of the coral and plankton that had lime shells at this time. Wildfires existed, increasing heatings, and ecosystems were destroyed at this time. And this marked the end of the dinosaurs, resulting in their extinction. And now we're moving to our modern era, Cenozoic. So we've moved from the Big Bang all the way to the beginning of the Precambrian through the Mesozoic, the Paleozoic, and then the Mesozoic. And now we're moving closer to modern day time with the Cenozoic era. Now, the Paleocene period lasted approximately 66 to 57.8 million years ago. And after the last mass extinction, mammals, birds, and insects became more dominant. The grasses were also dated approximately 57.8 million years ago, and the first apes appeared on this planet. So as we move forward, as from the Cretaceous period, you see the actual continents are starting to look like our modern day continents. And approximately 50 million years ago, Australia decided to drift away from Antarctica. And once 40 million years ago came, the Eurasian and Indian tectonic plates finally converged, resulting in a formation of the infamous Himalayan mountain range. And at this time, the Tethys Ocean dissipated. Now, 20 million years ago, Arabia started to drift away from Africa, resulting in the formation of the Gulf of Aden and the growing Red Sea as well. So lots of changes that occurred during that 40 million year period in terms of geological wise. So approximately 36.6 million years ago, flowering plants exponentially grew in great numbers. 34 million years ago, the temperature dropped, resulting in shifting of tectonic plates, lowering CO2 in the atmosphere. And during this period, mammals continued to evolve and were able to keep warm in cooler oceanic waters. Now, whales continued to grow, but it wasn't getting to sizes as big as our modern day whales till approximately 5.3 million years ago. Now, as baleen whales grew during the Miocene epoch, they fed on crustaceans at this time. Now, there was another mammal known as the Desmostylia, which ate kelp and seagrass in shallow waters. It disappeared during the middle of the Miocene epoch due to stellar sea cows and manatees controlling their food, leading them to their extinction. Now, another animal that actually got extinct during the Cenozoic was known as the famous woolly mammoth, which eventually evolved to elephants And as we see today, mammals continue to dominate during this period. So now we're moving to modern day. And now towards modern day geological time. Now, during the majority of the Cenozoic era, there was a seaway that linked the Caribbean and Pacific Oceans. When the Pacific plate began to converge against the Caribbean and South American tectonic plates, they resulted in the shape of Panama, resulting in volcanic and mountain building. And once the seaway was cut off, the salinity, which is the amount of salt concentration in the Atlantic, strengthened, bringing warmer water towards the north. And this closure resulted in nutrients forming, allowing a diverse number of corals and algae that live today. So as you see, they weren't always connected, and the ocean currents went through these continents until today. As you see, the warm waters moving up northwards, while the ocean currents continue to be affected by the continents and create major impact for ecosystems. Glaciation also had a big impact on ocean currents that we see and moved it in certain different places of the world that we see. But how ocean currents don't only affect the species of wildlife, however, they also affect how fast and where nutrients thrive as well. And this also impacts modern day hurricanes and where they go. And with El Nino, you'll see a little bit how hurricanes obviously form, usually towards the warmer water, like in the mid-Caribbean and off the coast of the Cape Verde Islands. And right now, we actually have 2 and a possible third tropical cyclone trying to form onto the west coast in the eastern Pacific Ocean. So modern day coral reefs, as we've talked about them a little bit and how they're usually formed there, they're formed each differently, and they're home to diverse number of species of animals. Now, over the Cenozoic era, the formations of each coral reef is different. So fringing reefs are usually formed around coastlines and continents and are apart from the shore by narrow but shallower lagoons. Barrier reefs are usually parallel to the coastline but are apart from shore by wider lagoons. Patch reefs, usually small, quite isolated, and usually form on the continental shelf or the opening of some island underwater. And another one which is called atolls, and they're usually found in the middle of the oceans and are ringed coral reefs that protect lagoons and typically form when islands begin to sink due to the rise in sea level and form usually on top of underwater volcanoes. Atolls grow and eventually are formed in a circle containing lagoons, and lagoons are shallow bodies of water restricted to the outlet of some areas towards the ocean. Now we move into our modern period, known as the Quaternary period, the Pleistocene and Holocene epochs. Approximately 1.6 million years ago, the earliest humans existed, evolved, and took over modern civilization eventually. It wasn't until 500 million years ago that the largest known coral reef to this day, called the Great Barrier Reef, formed off of the coast of Australia. Ice ages continued to form and go off, and the last one was approximately 10,000 years ago. And humans killed many species of animals, such due to pollution, hunting, and clothing, such as the Steller sea cow, which ended up in extinction in 1844 because it was being hunted. So as the dodo in the Galapagos. So the modern day continents, as we see, we've got 8 beautiful continents, or 7, but the 8th one is Zealandia, as geologists actually decided to make it a continent with New Caledonia off in this area. So I'm saying there's 8, but there's 7. As the Earth continues to grow mid-ocean ridges and gets recycled at subduction zone, our topography is still quite different and tells us these stories, such as ocean trenches, abyssal plains, and continental slopes and rises. We continue to learn today how geological oceanography has evolved over time, as we've seen in this movie, and affects modern day organisms and wildlife. And some of our wonderful modern day seafloor geology includes continental shelves, which you see, which are bordering continents, and they're getting to get steep, but the slopes are quite steep and they go towards the ocean floor. And then you've got the abyssal plain, which are flat ocean floors that tend to extend from the continents and actually lead towards abyssal hills, which are hills that are not usually larger than a kilometer in height. And seamounts are usually volcanic like underwater volcanoes that are not taller than 1,000 meters in height. And volcanic islands are usually formed by volcanoes. You've got hot spots when magma and material extend beneath the Earth's crust to surface, like Hawaii, which was formed approximately 30 million years ago. The continental rises are small slopes that extend from the base of continental slopes with the rise of continents, and ocean trenches, which occur when two tectonic plates converge in subduction zones, such as the Marianas Trench, formed approximately 180 million years ago by the subduction zone of the Pacific and Filipino tectonic plates. Now today, we have several zones of the ocean. We've got our wonderful epipelagic zone, and then the mesopelagic zone, bathypelagic zone, abyssopelagic zone, and the hadal zone, where most of the production of life occurs in the Nearctic zone, which is really in this area here around the continental shelf and continental slope here. And this is where most humans catch our fish, and where plankton likes to thrive up on the sunlight zone to get some food. The modern day composition of our atmosphere is composed of 78% nitrogen, 21% oxygen, 0.9% argon, and 0.1% of other gases. Now, we've got 5 layers known as the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. And it's important to us to understand because the atmosphere has a big relationship, as you've seen, with oceans, including their formation on rain beginning to fall onto the earth. Obviously, the atmosphere changed over time. However, it still does with the hydrological cycle, which continues to make a cycle with condensation, evaporation, sublimation, and continuing to bring rain on land. Now, hurricanes are one other thing that continue to use. They like to form on warm water and tend to be increasing in severity in the last 20 to 30 years. And it's just one of many natural disasters increasing in severity, such as this beautiful hurricane moving off the coast of the eastern United States. So as we move to the modern day oceans, to this day, we still don't know lots about the oceans. However, we've traveled through the past and explored how Earth formed and what processes it took to get to where it is today. Now, our oceans are filled with species of organisms divided into nekton, which are the swimmers, plankton, the drifters, and benthos, the seafloor crawlers. Humans continue to hunt for fish and destroy marine life. However, this is like geological history. The Earth cycles over and over to get to new beginnings. after these mass extinctions. And now we may be up for a sixth mass extinction, with the severity of natural disasters, climate change, and extinction of other wildlife occurring. I hope you enjoyed this and learned how the Earth formed and evolved over time in this presentation. And this presentation and movie here.